Hi everybody, my name is Alicia Ball, and today I'm going to be going over how to do problem 14.21c. And that problem states, at what temperature does the equilibrium mole fraction equal 0.5 for a pressure of 100 bar, assuming that the mixture is an ideal gas? And then the formula for that chemical reaction is given right underneath, and it's written right on there for you. So starting off, we're going to have to solve for z. And so this is going to be the equation that I'm showing right here, is how to solve for z with the given mole fraction that is equal to 0.5. So here you can see me plugging in the 0.5, and then we're going to use this equation to solve for z. And we get z is equal to 0.75. The second part that we're going to solve for is the reaction constant, and we're going to use the reaction constant equation for that, and also how we'll be able to see how the pressure relates into that. So we get z times 3 minus 2z squared over 1 minus z times 2 minus 2z, and that is going to be equal to k, which is the reaction constant, times the pressure over the initial pressure squared. And we should need to recall that we are given that the pressure is equal to 100 bar, and on the initial problem statement, the P naught is given as 1 bar. And so from here, we're just going to plug in our values of 100 bar over 1 bar squared and then times k. Then we're going to plug in 0.75 for our z values. And then we are going to be able to solve for k. And after we solve that, we're going to see that we get k is equal to 27 times 10 to the negative 3 as our reaction constant. And then the next part that we're going to do is going to be the net heat of the reaction. And so that's going to be the delta H for the total of the reaction is going to be equal to the delta H of the methanol minus the carbon monoxide minus the hydrogen. And all of these values were found for the enthalpy of reaction in the back of the book on those tables. And we get, for a total net heat of reaction, we get negative 90,135 joules per mole. Finally, our fourth step is to find the temperature at equilibrium. So we're going to use our equation for that, which is the natural log of K1 over K2. And K2 is found by the same as how we did in step number 2, and we just with the pressure of 1 bar for that initial pressure, and so we actually get just 1 second and it'll show up here. So we get 20,733 for that guy. And then we're just plugging in our values, our net heat of reaction value over the R constant value, because we assume that it's an ideal gas. 300 was our given temperature, and then our other values we solved for, and now we are solving for our final T value, which is going to be 516.5 Kelvin. And that right there is the solution for problem number 14.21. Thank you.